So let's tidy all this up. We're on 27 minutes already. This is a beast of a paper. Notice how they're all like question 7s and question 6s. All these come at the end of the higher paper. So all these are difficult questions. A Welsh company has been asked to design a toy that is able to launch a model plastic plane. They decide to use a spring mechanism in its design. Initially, they carry out an experiment to investigate whether a spring is suitable for use of the toy. So, first, for 4 marks, let's plot a nice graph, and I think for 4 marks this is nice. You've just got to be careful of the scale there, because your maximum is 8, well, it's maximum 7 there, and then you've got to go up to 22.5. So I've done my scale, and then I've plotted my results. They will try and catch you out, because they won't have, they'll miss some values, but for 4 marks, and for a mark, the length of the spring, state the length of the spring when no force is applied. Well, you'd have to just extrapolate that back there. I mean, maybe I should have said, I don't know, 4.5 there, but the mark scheme said 5, so my line's off a bit. So for 5 marks, I think, you know, considering it's one of the last questions on the higher paper, I think that's quite achievable. The design company decides to connect 2 of these springs in parallel with each other in a launch mechanism of a model plastic plane. The graph shows the extension of the spring system. State 2, the 2-spring system is stretched and a model plastic plane of mass 55 times 10 to the power 3 kilograms is attached. A trigger is pressed. Okay, so let's have a look what the question is asking. The 2-spring system is stretched to a maximum extension of 15 times 10 to the minus 2. Use a graph and an equation on page 2 to calculate the work done stretching this spring system. Give an appropriate unit for your answer. So at 15 is going to be there. I don't know if you can see it there. So I've interpolated and I've brought it back there to 12. So I've got, first of all, I need to get my equation. So where's my equation sheet? It's disappeared. Anyway, the equation I'm going to use is the work done equals half of the force times the distance there. Let's see if I can get this up, because it's quite important that I do this. I'm going to press pause a minute. There we are. I've just brought that up, and this is the one we're after. Look, we don't use it very often. W equals half the force and the distance. You can also do the area under, but I prefer using this. So let's use it. So I've got a force of 12, which I just calculated. Got from the graph. And then I've got an extension of 15 times 10 to the minus 2, which is from the question. And then it all comes out to be 0.9 joules, because energy is joule, work done is energy. And then health and safety guidelines limit the launch velocity of plastic plane to a maximum of 4 meters per second using an equation on page 2 and your answer from B1. Calculate the launch velocity of this plane when the mass equals 55 times 10 to the minus 3 and state whether the launch system design meets the safety guidelines. Oh, that's been a tough old paper. Anyway, let's crack on. So, where do I start? I'm going to start using an equation from page 2 and your answer from B1. So my answer from B1 was my work and energy come to 0.9 joules. So I've got energy there. And if you didn't believe me, there it is, though. Okay? And then I know I've got a mass of 55 times 10 to the minus 3. What's my velocity? Well, I know my energy and I know my mass, so it makes sense to use this equation. So I've got KE equals half mv squared. When I put that into a triangle, I move my KE up because all these are tied together. I'm looking for V, I'm looking for velocity. So it's going to be V squared equals KE over half m. So when I fill this out now, 0.9 over 0.5 times 55 times 10 to the power 3, which is my mass, that's going to give me 32.72 when I've done it, and then obviously I take this to get V on its own. Then I need to take the square root of 32.72, and that's going to give me 5.7 meters per second. Explain why the actual launch velocity is always less than your calculated launch velocity. Well, the plane has less kinetic energy because some of its energy is wasted. So, like sound and heat. So, you're never going to get that maximum there. So, some of it's wasted. We're almost there. Oh, this last one's a triple one. So, it doesn't apply for the doublers. And then you can read that if you triple. Oh, that was a slog.